that's the one that's so close and easy to kind of reference. Alright, so we have, everybody from 751 is here, and I don't know how many people are 141, so that's a really issue number.
I think he's got like 12. I don't know if there's that many that come though.
Yeah, I know. That's 2 inches of snow falling in a lot of areas. Yeah, moderate snow in a couple of hours. Pretty exciting. Okay, I think we're going to get started. Welcome to our weather discussion for, what is today? Friday, October 30th. Unbelievable. Today, we have Patrick Beatty and Alex Rao are going to give our discussion from 751. So please give them your attention and your questions. So take it away, Alex.
So, starting with the satellite image, we have, broad scale cloud cover over the New England region, coming back down over the Appalachians down into the Gulf of Mexico. There's some light cloud cover up in the northern Midwest from Manitoba probably over to British Columbia over there, and then relatively clear throughout much of the southwest. Or southwest. And then with our service observations, you can see pretty cool temperatures around freezing around the New England area. I think John mentioned that there's has been a couple inches of snow in Boston already.
Yeah, the highest amount I saw reported was 3.8 at Braintree, home of John Adams, both John Adamses.
Yeah, so it looks like further inland it's a little bit cooler enough for snow. Down towards the coast, looks like the air is wrapping around a little bit and it's a little bit warmer, 45. Over here, and precipitation extends all the way over to upstate New York over there, and then down into northeastern Pennsylvania. And a lot of this that's left is from the big low pressure system that came through this past week, which I'll be spending a lot of time on today. And also the remnants of Zeta have moved pretty quickly over there.
Yeah, in fact, is that feature that's labeled 994, even though we don't see any other data around it, is that the circulation center from Zeta?
Yeah, I believe so. So it's, I'll kind of do an evolution of what happened this past week, but there was a pretty deep trough that came through from the southwest and moved up over there, and it kind of interacted with Zeta, and it looked like they combined into one system.
Good.
So that's what that is up there. And then down into the southeast here. Lots of low to mid 50s, pretty cool. Down in Florida, once you get to the tip, it's still warm down there. It's 88 down at the very tip, and a lot of broad northwesterly flow still coming up over a lot of this midwestern region west of the Appalachians. And so, you see here, most of the higher wind speeds the highest wind speeds have moved to downstream of the trough axis. And trough axis is starting to lift out over into the Newfoundland region up here. And we saw some cloud cover over here, so
Where's here?
over Minnesota, Iowa, Illinois region.
Okay.
And I think this is at 12Z, and it's around 16Z now. So this feature has moved further to the southeast, and so this exit region of the jet to the right, we could expect divergence aloft, so likely rising motion.
Except it's counteracted by what? In that location?
Would it be the curvature?
Yeah, you're
Right.
just upstream of the trough axis, so they compete, they always compete.
Mhm.
Sometimes they interact constructively, sometimes destructively, and I think that the clear skies across much of the Great Lakes states probably means today that the exit region ascent is losing out to the curvature descent that's upstream of the trough axis. That's my guess.
Right. Yeah, I agree, because there's it does seem to be thinning out with the cloud cover there. And another feature I wanted to talk about is this sort of shortwave up near Washington and southwestern British Columbia. Patrick will be talking about this a little bit later on, but downstream of this trough axis here, there's some precipitation, and he's going to talk about the forecast for that a little bit later. Okay, so now I'm going back into the past. This is on Tuesday, 6Z the 27th, and this is 850 geopotential height temperature anomalies. So the trough that I was talking about before, that's moved over here. It was
Where is here?
Excuse me. The New England region,
Okay.
over New Mexico, Arizona, these southwestern states over here. 4 to 5 standard deviations colder than normal. So this system was pretty extraordinary in bringing cold air down, and I'll look at a little bit more why.
And in fact, if you zoom in on the 0 degree isotherm at 850, you notice that the further east you go, the less anomalous it is. Like it cuts through northern Maine, and that's not anomalous at all. It's just about exactly zero anomaly. But even over our part of the woods, central Illinois, 0 degree isotherm cutting through Champaign is about a 1.5 standard deviation colder than normal. So it jives with our own sensible experience. But it gets worse as you go to the southwest, as you're pointing out. I mean, that's really unusually cold in West Texas and New Mexico. Really unbelievable.
Yeah, and I found a graphic from, it's the Cheyenne National Weather Service, about the low temperatures that they broke. So this is on the 27th, and these dark blue bars are the observed temperatures that day, and then the lightest blue is the October record low, and then this is the daily low. So in Laramie, it was -26 observed, and that beat the daily record by a whole 10 degrees. Over in Scottsbluff, Nebraska, -10, that beat it by 21 degrees. So, like I said, that's something that's really unusual for this time of year.
Yeah, and it breaks in almost every case. Maybe the one exception is Alliance, I think, isn't it? That almost every other place, the current 27th of October beat the all-time monthly record low in almost all of these cases. Well,
Yeah.
some large fraction of them anyway. Unbelievable. Huh.
And over in, I think Cheyenne also, their weather service pointed out that they broke a snowfall record there too. It was 14 inches of snow in 24 hours, which beat their October record.
Maggie shares online that Amarillo got 5 inches of snow Wednesday night, Amarillo, Texas, and had a snow day and delayed starts in town.
Wednesday night, as Zeta made landfall
Yeah.
on the Louisiana coast, some 200 or 300 miles away.
Yeah.
Unbelievable. Or maybe more than that, depends on where. Where was it again?
Amarillo, Texas.
Oh, yeah, it's more than that.
Yeah.
But still, it's the same state. That's unbelievable.
So I'm going back all the way to October 24th at 12 Z. So this is Saturday, the day after we had our last weather discussion. So there's this really high amplitude ridge coming up into the Gulf of Alaska, and it sort of digs down into western British Columbia, and then there's this large zonal trough that covers, stretching from western Montana over to the Great Lakes region, and then back up to Canada and north of Newfoundland there. And if you look at it, it almost looks like an upside down omega, and it's almost perfectly symmetrical. And then also here off the coast of California, there's this low circulation contour. And if we move to the next time, that 12 hours later, it develops into a pretty prominent shortwave at 300, and we see that the jet streak here, upstream of the trough axis, is starting to allow that trough to dig. So on the exit region of this jet streak, to the left, we're going to expect upper level divergence. And also because of this trough curvature, ahead of that, there's going to be also upper level divergence. So you can expect rising motion, and this trough axis will start to sort of tighten its gradient, and it'll start to dig more. So we'll see the progression there.
Why is that going to happen, do you think? Thinking about the jet exit region on the upstream side of the trough axis, what you were saying some of the elements, but how do you put your argument together?
So I would say that the trough axis is located right over here, and if we have Washington, Oregon, Idaho, that area of, I guess, rising motion.
So what happens to the air column? Yeah, that's a good point. That Washington, Oregon, Idaho border, the point where they all three have a point, is a good spot to look at here. The air should rise there because it's in the left exit region of that northerly jet streak. What happens to the air as it rises?
It should start to cool.
It has to cool, yeah, because of the adiabatic expansion, right? So what's going to happen to the thickness of the column over that tri-state border?
It will decrease.
Yeah, so what do you think will happen to the upper level heights in response to the thickness decreasing?
They would increase.
No,
Or decrease.
they'll have to decrease because if the whole column's getting skinnier, then the upper level heights will fall too.
Right.
So, and that's a spot that's kind of important. It's right at the trough axis, and so if the heights are falling there, then you're right. The troughiness is going to be enhanced in that location. There's a reason you can make an argument for that,
Okay.
and you were dancing around it but didn't quite go there.
Okay, I see that. So I'm switching to some SPC archive maps. I noticed that a couple of the times are missing in the super feeds. But also this way we can also look at what's happening at the surface at the same time. So this is, so both these maps are at 300 at, on the 25th. So they're in 12-hour increments. And so the one on the left is the one that we just looked at. And like we just talked about, you can see the evolution over the next 12 hours. We did see the height start to fall, and you know, the gradient started to tighten. If we look at going a little bit further down, we should be able to see like we were talking about before, the temperature gradient. So where that jet streak was, this temperature gradient is you know, the tightest that you can see, at least at 500, in this general region of the trough axis. And we can expect from the thermal wind that you know, these wind speeds to increase because of that temperature gradient.
Well, you know, when you say that the wind speeds will increase, that implies you're going to look at a second map at a subsequent time and that there'll be a change in the speed. I think you mean the vertical shear will be largest in that location. Is that right?
Yes.
Okay, that's a different thing. That's all at one time, and it's just different levels,
Okay.
as opposed to the same level different times.
And then, you know, some of the surface observations here. So you can see downstream of that trough axis, we have a lot of snow starting to form from Wisconsin. I remember seeing a few flurries here on Sunday. And then going back into the Mountain West region over the Rockies. And you can see this broad northerly flow coming over the Midwest, and then a lot warmer temperatures coming up from Mexico, the Southwest region. And I mean, if you just look at this temperature gradient here, it's snowing at, I think it's Wyoming. It's 12 there, and then if you go to western Colorado, it's 55 degrees and clear. And so we're going to see how, as that trough moves, it's going to move the temperature gradient into, I guess, this sort of New Mexico, Colorado, Texas region. Oh, before I do that, I think I wanted to make a point that I think it's more of the along flow speed and the curvature that's moving this trough along. If you look at the center of absolute vorticity, so this is at 25th on 0Z, it's more of a bullseye area around the trough axis rather than you know, if it were to be oriented along it, and that's going to give us less cyclonic vorticity advection at 500, and I would still say that it plays a part, but it's not the main driver.
Driver of what, though? I've lost your train of thought.
Driver of digging this, I guess, trough to the south and bringing rising motion to get precipitation.
Over the high plains or something? I think there may be two separate questions. The the deepening of the trough maybe is controlled perhaps more by the transverse circulation at the jet exit, and the ascent that might spawn the snow that you saw in Wyoming and parts of the other high plain states is a result of being downstream of the curvature and the flow, and that can be related to vorticity advection. I think that's probably right.
Okay. So this is the next day, on the 26th. So again, looking at 300 millibars, 12-hour increments. From the last 24 hours, that jet maximum has seemed to increase even more, and the trough axis is even deeper. So you can see the whole circulation coming down over Western California and down into Mexico, and which is helping to bring a lot of this cold air down into this part, which is why we saw a lot of the anomalous temperature lows that I mentioned earlier. And so 24 hours from when we looked at the last surface observation.
Remind us of the time, though, Alex. We can't keep track of it the way you are, so tell us the time.
Sorry. It's this is at 12Z on the 26th.
Okay.
And so the Idaho, Wyoming, Nebraska area is pretty much clear, and we have lots of snow over Colorado, New Mexico, and even down into the panhandle of Texas. We have this warm air coming from the Gulf, and likely helping to bring more moisture into this area. So since we have rising motion associated with the trough, creating the surface low, and this moisture advection is helping to drive more precipitation in these areas, in this area over here. And you can see how sharp the temperature gradient is here, down towards the southern part of Texas. And it's 41 northerly, and then maybe 100 miles down, it's 78 degrees and easterly.
So is there some sort of a boundary in between those air masses?
Yeah, so I would expect a cold front to be along, I guess that's Texas, almost at the Texas border, moving up into it's northeastern Texas.
Yeah, right along the pressure trough that goes in exactly that spot, right?
Right.
And then there's a cyclone that's generated on the New Mexico-Arizona border that's kind of broadly trying its best, and it kind of extends to the southeast over the central states of Mexico, trying its best in response to the presence of the digging upper trough to drag the flow cyclonically around itself. And part of that cyclonic flow is the flow off the Gulf of Mexico that you're pointing out.
Right.
So you want to try to put these things in their broad context as best you can, and not kind of get lost in the weeds on individual pieces of it. That's the thing that makes the discussion really come together.
Mm-hmm. Okay. so this is on the 27th at 12Z. We have a closed circulation over the Arizona New Mexico border, showing how this is at 300 millibars, so how deep the system is, and where we have the surface low and the cold front that's moved through. It's brought it. It's the upstream of the trough access. Obviously, we're going to have the surface low, and
Downstream, you mean?
downstream, and bringing a lot of anomalous weather to Texas and Oklahoma over here. And this is around the time that, so this is 12Z, so around 6 a.m. on Tuesday, likely when Wyoming and Nebraska around that state border recorded those low temperatures that I was talking about earlier. So I would say it coincides with this region because we have this sharp curvature here going down across Colorado to Arizona, and then if we follow this isobar, this is the coldest region within that, or I guess the coldest region would be down here, but this whole area is it's bringing a lot of anomalous cold air.
Is that happening here at 300 millibars? Do you see any cold air advection at 300 millibars?
I guess not.
No, so you want to refer to the level of interest if you're going to talk about cold advection. That'll be easier for you to make your point.
So this is at 8:50 at the same time. We still have, I would say, a lot of warm air advection coming up along the southeast, and it is a bit difficult with the Rockies over here at this pressure level. Maybe I can move up to 700.
Yeah, it's probably a good idea because it is hard to make sense of things at 850.
Okay. I'll say that's a little bit better. So here we have -6 northerly flow coming over Nebraska, -7 at 700 over Colorado. So this is kind of I guess I would say the greatest region if you come over here, where cold air advection would be occurring. Because of that, because it's bringing that colder air from the north. I'll just try and wrap this up quickly so Patrick has enough time. But starting at 700, we can see Zeta start to move into the Gulf, and this low that we've been tracking, is now centered over the New Mexico-Texas border, and this is moving up into Louisiana, Arkansas, and this is still moving eastward. So that's when these two interact, and if I had more time, I would be able to show its movement tracking across the southern U.S. and up into where we see now, up into the northeastern U.S.
That's an interesting time, not just at this level, but probably other levels as well, because the large scale is so pronounced. There's a large scale trough and strong westerlies that have cut this feature off over New Mexico, Arizona, in Texas, and that itself is a large scale feature. I'd love to know if you took this as your initial time and ran 2 experiments. You run this thing forward, complete with zeta in there, and then in another experiment you erase zeta. You take it out and see how different it is downstream 3 days later in space and time. Because my first guess would be, and I know it would be stupid, it would be the wrong guess, but I'll say it anyway, that the large scale is so pronounced in this region of the Western Hemisphere that zeta won't have much effect. But I know that's not true, and I'd like to be able to exactly quantify the effect of zeta on the downstream forecast if that were possible. So it'd be a kind of a fun experiment to run if one could do it.
Yeah, that sounds interesting.
This is kind of around the time when Oklahoma was getting a ton of ice too. Somebody on the chat, one of our alum, Taylor DeWinter, said northwest of Oklahoma City they got 2 inches of ice.
No, that's miserable. That's the
Half an
worst
inch.
and most common severe weather element in the wintertime is ice.
A lot of people are still without power down there because of it.
Unreal.
Can I jump in for a minute? The
Yeah.
Zeta has had an effect of producing a fairly strong subtropical jet over the southeast. But unlike some other tropical cyclones, there's no real surge poleward all the way past 40 degrees latitude. It really stops right there
Yeah.
and then moves off to the east.
And that's because of that strong westerly flow
Yeah,
that comes down
it's-
across the border, yeah.
It's remarkable how strong the westerlies, the polar circulation is right now.
Especially here, yeah.
And holding off these things. And I think my guess is that is consistent with the La Nina we're in, and the very strong La Nina pattern we're in right
Yeah. There still is a 200 knot jet out over the to the east of maritime Canada today at 250 millibars, which I think is a manifestation of some of the.
now. I don't think it is.
It was yesterday anyway. Maybe I'm thinking about the wrong time.
Yeah, the jet really goes off at a low latitude. It doesn't
Okay.
push very far north. So I find that a little interesting because I've never noticed these types of storms like this before, where they just get sheared off at a low latitude.
Yeah.
And they don't penetrate.
Yeah, I think it'd be a fun experiment to run
Yeah.
to see what happens when you take zeta out, because maybe not much happens in this instance as compared to other instances. That's hard to imagine, but it might be true.
It's also interesting, and I think it's related, the fact that Zeta formed at all without a very strong easterly wave feeding.
Mm-hmm.
And there's another one that's going to form next Monday,
Yeah, that's what you were saying. Yeah.
Eta. And I don't know about after that, but they seem to be consistently forming in the Caribbean. And I think it's because there's cold air to the just not far from it to the north that's isolating the Caribbean as a warm bubble. And it's just driving the thermal circulation that's starting these things.
That's interesting.
That's what it looks like to me. I've never heard of that.
So persistent cold in the eastern 2/3 of the U.S. in the late hurricane season might sequester the Caribbean in a way that promotes development.
That's what that would be a wild theory, but
Yeah.
it occurs to me that something like that is happening, and that may be related to this La Nina situation.
Oh, interesting. Yeah, that is interesting.
There is some similarity between 2005 year because we have the same amount of hurricanes form in the season. So I was wondering the conditions could be similar compared to 2005, or
I don't remember what the fall around here of 2005 was like. So that's a good question. I wonder. That's a really good question.
Well, in 2005, that was the last time we had all these storms. Right?
Yeah, right.
And the Zeta storm that year was in January.
oh, okay.
So the 2005 season ended with in the Atlantic. It ended really with Wilma, and Wilma was over Cozumel.
Yeah. Early November we had Epsilon, but in the central Atlantic. I
Yeah,
remember that.
and
But
they
that
were
wasn't
off in the
St.
eastern
Louis.
Atlantic, and but they ended about here at the end of October with it was still a little earlier than this with Wilma, and then after that they were more sporadic. But it seems in the last several years I've noticed these Caribbean storms popping up at the end of the season, but not as much as this year. This is a little weird. Remember we had Mitch. It was a big Caribbean storm in the late '90s, and it hit Central America. Was it around Costa Rica or
Oh yeah,
Nicaragua
Mitch,
or somewhere around there? Caused a lot of death and landslide. It was a really big Cat 5 storm.
Yeah,
That was very late. That was in November.
yeah.
So they do happen in the late season, and I don't know if it has anything to do with the surrounding area being colder and creating this bubble of warm air over the ocean.
Yeah, it's curious.
Okay. Is this on? Okay. So I'm going to, like Alex said, focus on, see if I can zoom in, this shortwave feature that's going to be tracking right over southern Canada. And so this feature, it began in the Gulf of Alaska. Move the mice. And as it formed, it started to move towards the Alberta Rockies up here. And so as it's going to move over the Alberta Rockies, we're going to get lee-side cyclogenesis and an interesting storm that forms. So I'm showing 500 millibar heights in the black contours and then winds. And the winds are in the color fill. And so at this time, this is a forecast initialized today at 6C, so about 1 a.m. local time. And this is forecast 18 hours in the future. And so this is about 7 p.m. tonight. We have our shortwave that's going to be forcing the development for the cyclone and a downstream ridge over our area in this case. And so I'm going to use QG omega to diagnose first rising motion and then see if we can prognose how this storm is going to move. And so QG omega involves two terms. The first is the differential temperature advection by the geostrophic wind, and the other is the vertical derivative of vorticity. And so we can look at first 500 millibar relative vorticity, and I'll zoom in. And so this is showing the same time, 18 hours in the future from this initial model run. We have this strip of fairly intense relative vorticity, generally on the upstream side of that trough axis. And so if we think about geostrophic relative vorticity advection, right downstream of this maximum in relative vorticity is where we expect the maximum amount of geostrophic relative vorticity advection at 500. And so if this geostrophic relative vorticity advection is stronger than that at a lower level, we can expect to see rising motion in that region just downstream of our ridge, or our trough at 500, excuse me. And so I'll show 700 as well. At the same time, zoom out a little bit. There we go. So in that same region, we're looking right about through Montana into Saskatchewan. There's still positive vorticity advection occurring from the geostrophic wind in this area, but it's not as intense as it was at 500. So we should expect that from the geostrophic relative vorticity advection, that this forcing would be forcing rising motion just downstream of the trough at 500 and 700 hectopascal. And so then the other term we can look at is the temperature advection. And I'll zoom in. And so this is that at the same time, Saturday, 0Z, we have in the region that we were looking at for positive relative vorticity advection in this Montana to Saskatchewan, we don't see a lot of differential temperature advection. So one of the things that we need is we need it to be differential. And it seems fairly uniform warm air advection in this region. So by that, I would guess that the temperature advection is not forcing a lot of the rising motion. It's mainly due to vorticity advection, and that might be working to not create rising motion or working against rising motion in that region. But we do see, this is our system and our 850 minimum and geopotential heights. We see that from this time, we have a fairly substantial warm boundary with air rising from the south to the north, and then we have a beginning of a wraparound around the minimum and heights along the Alberta Rockies. And so at this time, we have pretty substantial differential temperature advection occurring just downstream of our minimum and heights. And so we should expect that potentially we might have rising motion occurring in this area, which would allow us to say that we should expect our storm to move that way. So if we go back and focus in on that area, it was in like central Saskatchewan. At 500 millibars, there's some vorticity advection. It's not as intense as the vorticity advection lower towards the trough axis, but there still is some vorticity advection occurring, especially, say, between 537 and 540 decameters. There is a band, there are some regions of positive vorticity advection that are substantial, and then if we go to 700 and look at that same region, there's generally weaker vorticity advection right up in this region in south central Saskatchewan. So in this region, we could say, okay, we might have rising motion occurring, and we should expect our cyclone to move generally towards that region. So if I pull up 18-hour forecast, I'll zoom in. So this is 18-hour forecast QG omega, essentially what we just diagnosed. In the region where we had the vorticity advection and the temperature advection working together, we do see rising motion. So yellow contours are rising motion, green are sinking motion, and then the dotted lines are the 900 to 500 thickness contours. And so we have generally warmer air to the south, colder air to the north. So in this case, our cyclone centered somewhere, maybe at the Alberta-Saskatchewan border, and directly or downstream of that cyclone center is where we see our rising motion. So from this, we could say, okay, we might expect our storm to generally track zonally towards the east, because that's the maximum in our rising motion. And we don't see a lot of rising motion back behind upstream of our system. And so I will pull up our second time now. Doing generally the same idea. So this is stepping 24 hours in the future. Zoom in. So this is now Sunday at 0Z, so 7 p.m. Saturday night. We see a very intense 500 millibar trough with a wind speed maximum upstream in the trough. And from this, we might expect our trough to dig. So we have intense winds on the upstream side and weaker winds on the downstream side. So all of this momentum is going to be driving the upstream side down, not as quickly as the downstream side is going to be driving momentum upwards. So our trough is going to dig, and this coincides with where we have, if we think of our cyclone centered somewhere Western Ontario, we'll have a lot of cold air advection being pulled down from northern Canada towards the northern United States. And so if we have cold air advection blowing up against warmer air that was situated there, we should expect winds to increase because we will have an increase in the thermal wind, the thermal gradient, and then an increase in the vertical shear. And so at 500, we see that. We see this increase of winds upstream of our trough axis.
Patrick, I think you're trying to say too much about this one chart. There's a whole bunch of things that you're talking about, and it's probably better to illustrate some of those elements with other charts
Okay.
that are at the same time. The other thing is, though it seems conceptually appealing to suggest that because the wind speed is stronger on the western side of the trough, that will make the trough dig just by momentum on the west side being greater than on the east side. It seems to suggest that it's geopotential height advection that's digging the trough, and that's really not the case. I think instead one has to think about how's the mass field being rearranged as a consequence of the stronger wind speed on the western side of the upper trough versus the eastern side, because that's a valid point. That foundational point is valid, but the argument's not so airtight. I think it's more along the lines of you've got a thermally indirect vertical circulation at the exit region of that stubby jet streak over the Dakotas,
Right.
and the consequence is the air is rising where it's already cold, and so you're going to you're rearranging the mass field in such a way as to lower the heights in
Okay.
that rising column. And that's probably what digs the trough more than, simply advecting geopotential heights more vigorously on the western side than the eastern side.
Okay, that makes sense. Okay. So from the 500 millibar heights, I will step forward in both vorticities. So I'll zoom in. So at 500, we have a more broad vorticity around our trough at 500 millibars. Generally, Minnesota into western Ontario, we have stronger positive vorticity advection following the geopotential height lines, and then down towards our region, which may be some semblance of a cold front as the cold air is wrapped around the backside of this trough, and that might be producing some of the positive vorticity advection that we see stretching further down towards Kansas, Missouri, Iowa, and Nebraska. And so we can do the same thing where we go from 500 to 700. And I'll zoom out and step forward 24 hours. So again, this is Sunday at 0Z or Saturday night here. Keep zooming in. Okay. So at the same time, we had Minnesota to western Ontario is where we saw the maximum positive vorticity advection. In this case, we see maybe the same vorticity advection, maybe slightly weaker towards Minnesota, but definitely weaker into Ontario, and then sort of the same cold front with the positive vorticity further to the southeast than it was at 500. It was more back along the line from Kansas to Iowa. And so from this, we can say we might have some vertical motion from the positive vorticity advection and the differential of it across Wisconsin, Minnesota, Iowa, Nebraska, and then potentially some into Ontario. And so we can look at the the temperature advection at the same time. And so we begin to see a fairly substantial storm forming and taking place. Substantial cold air advection wrapping all the way from Montana down into Nebraska and then up towards our state, with warm air advection upstream or downstream of the 850 geopotential height minimum, excuse me. And we need differential temperature advection or, of course, rising motion. So we do see there's differential temperature advection occurring from Michigan down towards Nebraska, and then also up towards Ontario, central Ontario, and eastern Ontario. And so based on this, we can diagnose, maybe we'll see some negative omega, QG omega, and then negative QG omega as well up into Ontario, which will say we have rising motion in that region. And if we go back to the QGeo megaplots and go to the same time. I'll zoom in. We do see sort of that pattern set up. So we have, this is along our cold front and cold air advection, and then we have a maximum in rising motion into eastern Ontario. And so, like happened 24 hours ago, if our cyclone centered eastern Ontario and our maximum in rising motion is just zonally to the east, we will expect our storm to just continue to move easterly at this time, and it does so, and it continues to move easterly until it gets into maritime Canada for like into Monday and Tuesday.
Can we split this up into the shearwise and transverse pieces?
Yep.
Since you've had an emphasis on the frontal pieces, so let's look at the shearwise one first.
At the same time.
Yeah, at 42 hours. So this is just the piece that has to do with the convergence of the Q vector along the isotropes.
Correct.
So there's no frontogenesis implied in this at all. Okay, then let's see what the frontogenetic piece looks like. Because that gives roughly the same structure as you see for the total.
Right.
Sometimes the frontogenetic part, which is not well resolved by the quasi-geostrophic equations, looks like embroidery. But look at that. You get a nice piece along the warm front and a nice piece along the cold front, as you suggested. And then there's subsidence forward of the warm front over Hudson Bay. So that's a...
Right.
The scale is too cartoony, but you do get to see a little bit of what's going on there
Definitely.
when you split it up.
Definitely, yeah, I forgot to mention those. And we can look at now, so I'll just step through briefly what I was showing. I'll zoom in if I can. So this is our storm. This is from the first time I showed, so 18 hours in the future from the model initialization. And at this time, we don't have a well-defined cold front, but we do have some hints at a warm front developing, and our precipitation is located generally in the region where the warm air flows up into the cold air. And then I also thought that because we have leaf side cyclogenesis, a lot of the air that this storm is going to pull down on its backside is going to compress as it sinks towards the surface and lose a lot of its moisture. And so at this instance, I would expect there to not be a lot of precipitation on the backside because it's too close to the Alberta Rockies. So as it moves and continues, it'll be able to pull in some of this wraparound moisture from the north side, and then also, just generally get away from the mountains and have more moisture, not affected by adiabatic sinking or rising.
You know, I think the more conspicuous difference between an Alberta Clipper lee side trough type development like this one is, and the classic comma shape, is the trailing cold front structure is absent right now, as you point out. There's nothing there. It's kind of a warm axis, and that's characteristic of a lee side trough. But there's also no precipitation along that boundary, that troughiness. And the reason is because the air is too dry, and there's not any particularly well organized ascent along the trough. It's all out to the north and east in the differential warm advection. So that's a different way to think about that.
Okay, yeah, that makes sense. And so I'll step 24 hours ahead, where we began to see frontal structure. Let me zoom in. I'm able to, here we go. So we have continued precipitation occurring along the north and now the northwest side of our surface cyclone, and then some precipitation beginning to form along the cold front. Generally, the precipitation stays along the zonal line as it tracks towards the east and towards maritime Canada. And so some of these locations in central Ontario, Saskatchewan, I can zoom out, maybe. I'll pull up the snow totals and go to 42 hours. They get up to 16 inches of snow just from this storm that formed. Doesn't have a lot of influence from the Gulf as it's initially moving, but there's still plenty of moisture to form a band of snow up central Saskatchewan that's up to 16 inches of snow. So
Can we look at the 10-to-1 ratio? Kuchera is a little bit
Yeah.
steroidal
More
when it
wish
comes to
cast.
forecasting snow. 'Cause it'll be a little bit less. So it's still substantial. Okay,
Yeah.
sometimes there's much bigger differences between these two. Okay.
right.
But that's a strip of snow across central Canada. That's not something you want to see happen in late October if you want it to get warm here again. But I don't. I'm glad to see it. But
Yeah, me too. And then, let me see how come. Okay, so then I will focus on where the storm goes. Let me pull up Vision Map, and then I'll zoom out to look at just North America. And so here's our storm. Let me zoom out a little bit. There we go. So here's our storm we're looking at. It's 992. This is 42 hours into the forecast with thickness lines dashed, precipitation, and then our pressure contours. And so I'll step ahead 24 hours. Let's see. Okay, so at this time, our storm weakened a little bit, so having troubles in it. There we go. So it's 995, and we see this upstream downstream cyclone, fairly anticyclone, yes, fairly substantial, and so we have a lot of cyclonic flow and an anticyclonic flow converging to bring moisture and forcing for rising motion up, generally where the storm is tracking, and so I'll go 24 hours from this time.
I'm not
so
sure there's much forcing for rising motion there. That looks like uniform warm advection. That's the one weird example, and you can convince yourself of that when there's no divergence of the gradient of temperature advection, and there probably isn't very much of it in that southerly flow that goes up over maritime Canada. Then you get no vertical motion forcing.
You're talking about like right here?
Right in there, yeah.
Yeah, okay.
It's got to be differential temperature advection to make it work.
That's right. Okay, so I will step forward 24 hours. So at 995 is our central pressure. And then 24 hours in the future, we get 30 millibars of deepening to 965. And if we go 12 more hours from this time, we get down to 949. So a storm that started out looked like it was weakening as it tracked easterly towards maritime Canada, and then explosively developed 46 millibars in 36 hours, with the upstream or downstream anticyclone also strengthening. I have 2 minutes left.
So yeah, can I ask you, Patrick? Maybe
Yep.
you've got a plan, but can you show us the 500 millibar evolution over these two times?
Yes.
And I'm interested in just really the geopotential height. The vorticity here is just so sinuous and weird. Just nice to see what the upper structure looks like.
Yeah, let me step back. Okay. I zoom in. There we go. Okay.
So that's a potent upper trough. That's definitely a potent upper trough. But the trough axis and the main wind speed maxima associated with that trough is well south of the position of the cyclone at this time. It's kind of a confused what is this? This is Sunday night. So but it's quite confused. There's a little troughiness over eastern Hudson Bay, but the deep trough is just south of Lake Huron. And that's the disjuncture. The cyclone doesn't know what to do at this stage because it's got a little bit of forcing from both of those waves.
Definitely, yeah. And then I can go 12 hours to see how it zoom in. So around the base of the trough, beginning jet streak sets up right off the eastern coast and into maritime Canada. The trough requires a more negative tilt in this sense, so fairly intense diffluence and positive vorticity advection right over Nova Scotia, Newfoundland, and this is right around where our storm begins to strengthen and eventually reach its minimum, local minimum or like extreme minimum up right off the coast of Greenland and Canada of 949, and we'll go, I can go 24 hours from this time.
I think 12 hours would be more
12 hours?
instructional. Yeah, let's see what that says. Yeah, I think you see what's happening here. There's only one trough late in the evolution of this thing. There's not really two, so the cyclone can get itself better organized, and the wavelength between the upstream trough axis and the downstream ridge axis keeps getting smaller as the precipitation shield, presumably as the precipitation shield from the cyclone gets revved up in the Labrador Sea.
Right.
So there's a nice diabatic feedback implied by this that
Can we-
we'll talk about
Can we
later on
jump
in
in
our
for a
class.
moment?
Yeah,
Guess what?
but
This is exactly coincident with the first time that the polar night jet has appeared.
oh, is that right?
And
Late October.
it's connected on both of those ridges
Mhm.
at this point. It's continuous down. So now we have a very deep and suddenly strengthened jet stream by merging with the polar night jet aloft. And so I'm guessing, I don't know this, I'm just noticing this last couple of years, these two velocity maximums that are appearing here and getting stronger are continuous all the way up, and they're being forced by the deeper, stronger ageostrophic circulation around the combined polar night and polar jet that's occurring on those ridges up there, because that polar night jet goes right across those ridges and is continuous right down to those ridges, not into the trough. And we saw that last year. Remember when they connect, boom, we get these bomb cyclones and all these things
Yeah.
happen. I'm guessing that has something to do with it.
Well, it might be.
Yeah, definitely.
This is the first time they've connected this year.
It's interesting.
Let's see. Okay, I'll just make one more comment. If I step, just looking at surface pressure and then go all the way in the forecast, I think it was Ada that was mentioned. It lingers around, and this is a model guess, and well into the future. This is November 15th, so 384 hours out, but Ada lingers along like the Central America coast and begins to make a turn towards the United States. So we might have another system affecting Yucatan and then into Louisiana.
Louisiana.
That might be IOTA,
Yeah, right.
Over
That's
there.
so far in advance. That's the one after the next one.
because I think Ada, they were showing something around, if it was a named storm, around the 3rd or 4th.
I noticed it like it forms and then it dissipates somewhere over here and then it forms again
Yeah,
and continues to sort of meander. So yeah, it might be two separate storms or
I looked at that in the ensemble. The ensemble was pretty tight on it, that
Right.
something was going to form.
yeah. So are there any questions?
Any questions or comments before we adjourn? Okay, thank you guys. And thank you,